our speakers today. I'm an astrophysicist here at the Smithsonian Observatory. So when they asked me to do this, I was really excited. The first thing I did, as you might do, is go and look online at these people that are here today to talk to us. And when I was looking at Daniel Whiteson, I read that he's a professor at UC California, or University of California in Irvine, that he's currently an APS fellow, American Physical Society fellow, that he was a Fulbright fellow, and I was like, wow, that's amazing. And then I looked up Jorge Cham, and I read about him. I knew about him already from his PhD comics, but he did his PhD at Stanford University in robotics. And I said, wow, robots, that's amazing, that's cool. This is just like overwhelming, this is great, it's gonna be awesome. But he's more known now for his comics, for his PhD comic series that really sheds light into this world that a lot of us go through, those of us who were grad students and studied our PhDs. And I started thinking at that moment, why did they pick me to do the introduction? I started grasping for ideas, reasons why. I also learned that Daniel Whiteson did his undergrad at Rice University, which is in Texas. I'm from Texas, so okay, we have something. There's something I can hold on to. And it turns out I also drew comics when I was in grad school, but they weren't the type of his. They were more kind of very self-serving, like the titles. One title was March 31st, and it was all about March 31st. And it really was just a diary in illustrated form. I think I talked about a carrot ginger soup I had that was delicious. But then I started thinking, how did you know all these things about me? How did you know I was such a good fit? And I thought about the background check I had to do to get this job. And suddenly I started wondering, oh, how deep did they go? And why did they still hire me after the depths of things that they must have found or uncovered? But no, that wasn't at all why I was invited. I haven't found out why exactly still. But what we are all PhDs. We are all close in age to that, getting that PhD actually. It's not that far in our history, and we're still steeped in that culture and the idiosyncrasies of that culture and all that it brings to us as PhD students, people who've gone through the turmoil of this process. And I'm displaying for you now one of those characteristics of imposter syndrome, like, why did they pick me? I'm not worthy. A little bit of that. It can be a lot worse than that, trust me, though. But they did pick me, and I'm here, and I said yes. And I said yes, not because I knew I could do it, but because I didn't know if I could do it. And there was only one way to find out if I could, and that was to actually do it. And we're all here today because we have that same spirit of trying to figure something out. That's why you're here. That's why you attend these events. That's why you watch them virtually. And we're really grateful for that. And we're grateful for our speakers today because they're going to shed some light on the things that keep scientists and physicists up at night. Those things that we don't know, the things that we want to learn, and the things that we absolutely have no idea how to figure out. And so without further ado, I'd like to bring up Jorge Cham. And while we're at it, let's also give a round to Daniel Whiteson.
Hello! How's it going? Oh, come on, we can do better than that. I'll try it again. How's it going? All right, much better. Well, not that much better, but no, I'm just kidding. Great. Well, first of all, I'm going to thank the Center for Astrophysics for inviting me here today, me and Daniel here today, and sponsoring all these great events for you guys every month. Let's give them a round of applause, please. And thank you to all of you for coming to the event. I know it's a Thursday evening. It's a beautiful night for Cambridge. But we're really happy that you're here. So my name is Jorge Cham, and I'm here with Professor Daniel Whiteson, and together we're the co-authors of this book called We Have No Idea. Now, I am a cartoonist. I draw comics and cartoons for a living. And to me, cartooning is about taking a blank page and filling it with an idea. And so the idea we want to draw out for all of you here tonight is this idea that there are still big gaps in our knowledge of the universe. So in addition to being a cartoonist, as was mentioned, I'm also a roboticist. I have a PhD in robotics from Stanford University. Now you might be wondering, what does having a PhD in robotics have to do with being a cartoonist? Well, I can tell you that my parents are also very concerned about that life plan there. I did a PhD in robotics, and in fact, my thesis work focused on making small robots that could run like cockroaches. Yeah. So today I'll just kind of tell you a little bit about how I went from robot cockroaches to working with Daniel, and then Daniel's going to come up here and take over, and he's going to tell you about the ideas inside of We Have No Idea. My research was on robots that could run like cockroaches, and here's a quick movie of what these robots look like. Yeah, that's what I did for my PhD, and I like to show. I can't tell if that's a sympathy applause or a excitement applause. We have a question already. All right, let's see.
Were you the one punching it?
Yes, I was. I was the one punching it. Yeah. It's a robot, though. Didn't have any feelings yet. But no, I like to show this movie of what I did for my PhD for two reasons. First of all, I feel like this movie really represents, really captures what it feels like to get a PhD. Maybe some of you in the audience kind of know that feeling. You feel like you're running the whole time, but you're not getting anywhere. Meanwhile, there's a more intelligent being stamping you down. But no, I also like to show the movie because it's the only way that anyone will look at my research. Gotcha. No, because a little bit more popular, I think, throughout the years, I found a lot more popular than the research I spent years on, has been what I did when I should have been doing research, when I was kind of procrastinating, drawing comics, these comics called PhD comics, or Piled Higher and Deeper. And so these were just comics that I started kind of on a whim while I was in graduate school, and they were kind of about the graduate school experience. Some of the begging that you have to do when you start out and you want to join a lab. The comics were about being a teaching assistant. And they were also about learning graduate student etiquette. Never ask a graduate student or scientist how their research is going. Just a small tip there. Yeah, so these were comics that I drew, and at some point I started posting them on the internet. Just kind of put them on a free web server on campus there. And I think as most of things that you hear about on the internet, pretty much what happened was people who read it there and liked it would then tell their friends that they knew in other universities, and then those people then tell their friends and their coworkers, and then those people tell other friends in other universities. And so slowly over the years, kind of like a virus, these comics kind of made themselves a way out into the world. And to the point where these days about 6 or 7 million people visit the PhD Comics website, which is a staggeringly small number, actually. If you think about the fact that there are 7 billion people on the planet, so there's about a 1 in 1,000 chance that you may have seen these comics before. But it just so happened that one of those 1 out of 1,000 people that saw these comics on the internet out there in the world was this professor at the University of California at Irvine, Daniel Whiteson, who decided one day to just email me. So one day I just get up and I check my email, and I get this email out of the blue from this professor. And this email said that he introduced himself as Daniel Whiteson from UC Irvine. He said, "Jorge, I've seen your comics on the internet. I think they're pretty cool. I'd like to pay you, I'd like to commission you to draw some comics about the Higgs boson. And so I thought, what? You want to pay me? What is that? I don't understand. I just put things on the internet for free. I don't understand that concept. But I said, yes, of course. And what happened was that Daniel had seen a lot of the press surrounding the Higgs boson discovery, leading up to the discovery. This was a couple of years ago. And he wasn't satisfied with the way journalists and writers were kind of describing this research and why they were searching for the Higgs boson. And so he decided to take matters into his own hands. And so he decided to contact the cartoonist and offer to pay him to draw something that explained what this Higgs boson was. And so I said yes, and so I went down there and when I interviewed him for a few hours at the cafeteria there. And then when I went home to draw the comics, I decided to experiment a little bit. And I took that audio recording and I kind of edited it and I mixed it with some of the recordings of me drawing the comics. And so we made this kind of mix of a comic and a video, which I'm going to play for you now, a couple of minutes of, just to kind of give you a sense of how our collaboration started. So here's a little bit of that video.
So one of the things people predict is the Higgs boson.
The idea is that the Higgs boson is the particle that is responsible for giving mass to the other particles. So you think of things when they have mass means it has stuff to it. It's not actually stuff. Earlier I was saying an electron has mass, but has no volume. How can that be? Turns out mass is probably just a characteristic of a particle the way like charge is. Like some particles have charge, like electrons. Some particles don't. It's just a different kind of charge. So you can think of mass as sort of gravitational charge. And when two things both have mass, they attract each other. Interestingly, you can't have negative mass or repulsive gravity. So, all right, so the collision happens. It lasts for like 10 to the negative 23 seconds, and you get one measurement, right? So if you say, well, I'm going to plot the mass, the total energy of this guy. I'm going to add this guy and this guy together and add the total energy. This is this axis here is number of collisions. You do an individual experiment, you get one measurement, right? Here. You do another one, you get another measurement. You do another one. Eventually you build up your data, right? And the data looks like this, for example. And then you have two theories, right, that predict the data. One says, well, I'm going to predict there's no Higgs boson, so the data should fall along this line. And the other is I'm going to predict that plus a Higgs boson. And the problem is the difference between these two theories is very small. And so it's very hard to distinguish these two with our data because the predicted effect is tiny, right? If the predicted effect were huge, it'd be very easy to tell the difference between with Higgs boson or not with Higgs boson. But the predicted effect is tiny, and so it's really hard to see. What you need is a huge amount of data. You need to take a bajillion collisions before you can see the difference. That's why we run this thing 40 million times a second, all day, all year, to get a lot of collisions to tell small differences between things. It's like when you take a picture of the sky. You just take a picture, you get a little bit of light. The longer you leave a telescope looking at the sky, the more you can see farther away things.
Yeah, that was our first collaboration, and so we made these comics and video, and then we've just posted them on the internet. We took a little bit of a risk, and we posted it on YouTube and on the PhD Comics website, and people really seemed to like it. They enjoyed it, and it got a lot of views. But then what happened was they actually discovered the Higgs boson a few months later, and then that's when the video really sort of exploded. Millions of people watched this video, and it got reposted and relinked to by the big websites like the New York Times or CBS News. And everyone was calling this the clearest and most easiest to understand explanation of what this Higgs boson was. And so I thought that was really cool that, the clearest and most easiest to understand explanation of what this kind of complex phenomenon was, it didn't come from a writer or a journalist in the New York Times or a media person at CBS News. It came from actually one of the scientists who actually worked on the project, who decided to take that initiative and sort of try to communicate that his work directly to the public. And so I thought that that was pretty cool. So that was our first collaboration, and that kind of led to a couple of other projects, the latest of which is this book called We Have No Idea. And so here to talk to you about the ideas in We Have No Idea is Daniel Whiteson.
Hello, everyone.
been a real pleasure working on these projects with Jorge. Not only is he an amazing artist, he's also really modest. So, for example, I have to correct the story a little bit that he told you because he leaves out some important details. When I thought about explaining physics using cartoons, I thought that would be a lot of fun, but I don't have the artistic talent to do it myself. Who could I get to do this? And my wife, who's also a fan of PhD comics, she said, well, why don't you email Jorge Cham? And I thought, well, Jorge's not just some cartoonist, right? He's like, in academia and in research, he's world famous. You can't go to a lab that does research and not find one of his cartoons on the wall. Because he's really captured, the experience of being a graduate student and the suffering of research and all of these things. So it's like just emailing a famous person, right? So she says, why don't you email Jorge Cham? And I thought, sure. And then I'll call Brad Pitt and ask him to make a movie about me, right? Like, while we're at it, right? So I still haven't heard back from Brad, but I did get to write this awesome book with Jorge, which is a lot of fun. So we're here to talk to you about this book, and a lot of books about science are mostly about what science does know, what science has figured out, which is a lot of cool, awesome stuff. But for me, science is more about learning than about knowing, so we thought it'd be fun to write a book about all the things that we don't know about science, right? But when you come to hear an author talk about their science book, you expect to hear from an authority in the field, right? It's a book about biology, you want to hear from a biologist. So if this book is about not knowing things, then what's my expertise, right? Like not having ideas or not knowing the answers, we're all experts at that, right? So it's not that I'm a special expertise in ignorance, right? It's that I really want to emphasize this joy of future discoveries, because everything we don't know is something that we can figure out. And so that's the focus of the book. And it really comes from when I was a kid and I was reading about the Age of Explorers. And to find something new, these guys just had to jump in a ship and sail across an ocean, and they could land on a new beach, right? Somewhere no one had ever walked before. They could eat a new fruit that nobody had ever tasted before. And I wanted that for myself. I wanted to know something and be the first person. I wanted to touch something the first time for a human. Imagine what it must have been like to be the first human to ever see the Grand Canyon, right? Somebody got that. Or the first person to ever taste chocolate. Or the first person to ever eat chocolate while looking at the Grand Canyon, right? These are all first in human history, and I wanted one for myself. But as I grew up and I learned about, Google Earth and satellites and all this stuff, it feels like all the continents are pretty much taken, right? You can't just jump in a ship and expect to land somewhere and then name that island after your dog or anything. It's mostly used up. And then as you look around and you learn about all the amazing things that science has figured out, you might get the feeling like science has basically tied up all the loose ends. Like we have incredible airplanes. You can fly across the world in just a few hours. You can download almost all of human knowledge onto a tiny little device. Truly, we live in an age of wonders, right? And you might get the impression that science is a day or a week or a month from figuring all this stuff out, right? This is as close as I get to Brad Pitt right here, okay? And so you might feel like science isn't mostly figured out, right? But the point of our book today, and the point of our presentation this evening, is to convince you that the exact opposite is true, okay? That actually we are at the beginning of a new age of exploration, a new era of discovery, when we're going to discover things that will totally blow our minds about the way the universe works. Because we've recently learned how little we actually know about the universe, right? And so the book is about sharing with you that excitement, because every time there's something we don't know, that's something that we could potentially learn, right? I got the clicker here, so I got to cut you off. So what kind of exploration am I talking about? Because if you're dying to explore things, I'm disappointed to tell you there aren't any more islands out there, right? So what kind of exploration? I mean the kind of exploration that answers really big questions about the universe. Really big, fat, juicy questions. Questions where if you knew the answer, it would change the way you felt about life, right? About the whole context of humanity. About the way it might change the way you live your life, right? So what kind of questions am I talking about? Questions like this, like, why are we here, right? What happens after you die? If you knew the answers to those questions, like really knew it, it would change the way you lived your life, for sure, right? These are big, deep, important questions. You don't have to be a scientist to want to know the answer, right? Or we have another question up here. What is it like to be a bat, right? And you might think, well, that's a joke. Surely that's a joke. It's actually the title of the most widely cited philosophy paper of all time, okay? It's a serious academic philosophical discussion.
And that's the problem with these questions, is that these are philosophy questions, right? Which means that you can think about them, you can talk about them, you can smoke banana peels for 20 years, but you're still not necessarily going to make any progress, right? People are still talking about these questions, right? And they will continue to talk about these questions for a long. The bats are not supposed to be smoking, Jorge. No bats were injured in the making of this book, okay? Right? That's the problem with these questions. We want to know the answers, but there aren't necessarily answers. But to me, the really exciting thing is that there are other questions at the same gut level of importance, right? But these are science questions. Questions like, what is everything made out of? Or, how did the universe begin, right? Take that one for an example. There is one true story about how the universe began. Happened one way and no other way, right? And if you knew exactly how the universe started, that might really change the way you thought about your life, right? Or how you lived it, or the whole human experience, right? And the amazing thing is that there's an answer and we can figure it out. If we sift through the rubble of the Big Bang or do the right experiment, we will learn the answer. In 100 years or in 10 years or in 1,000 years, somebody will know the answer. And they will look back at us and say, what was it like to live before we knew XYZ, basic facts about the universe that we're totally ignorant of, right? The human experience will change once we know the answer. The answer exists and we will figure it out. Okay? So to me, that's really exciting. That these are big questions. You don't have to have a science degree to understand why the question is interesting, and we know we will figure out the answer eventually. So let's talk up tonight. I want to talk about one of these questions, which is this one. What is the universe made out of? To me, this is a pretty interesting question. It's a basic question. It's also a reasonable question, like to want to know the answer to, right? As a conscious being, like, I want to know what I'm made out of, what you're made out of, what are my shoes made out of? Like, what is the whole organizing principle of all of this stuff? I also think it's probably a pretty ancient question. I think people have been asking this question since people have been asking questions, right? Since people like bang rocks together and get smaller rocks, and then they take those two rocks and they go, bang those together and get smaller rocks, and wonder, how long can I do this for, right? Do I get infinitely smaller rocks as I keep going and banging these tiny pebbles together? At some point, does it stop being rock, or do I get the smallest possible rock, right? This is like how particle physics was born, you know? If particle physicists are superheroes, then this was our origin story, right? This is how it all began for us. So imagine that you are caveman or cavewoman physicist, okay? And you were the first person to ever conceive of this question, right? What is the universe made out of? How do you attack such a big question? Often in science, we start with a big question, but we end up working on the little narrow questions, right? Because those are the ones we can tackle. How do you tackle a really big question? Well, my approach in science when I'm facing with a really hard problem is try the dumbest thing first, okay? If that doesn't work, then try the second dumbest thing, right? So what's the dumbest way to approach this problem? What's the universe made out of? Well, try just making a list, right, of everything that's in the universe. So, all right, make your list of stuff in the universe, okay? I'm in the universe. You're in the universe, right? We're cavemen physicists, so there's rocks in the universe, right? All this kind of stuff. And pretty quickly you're going to see the problem with this approach, right? First of all, there are a lot of rocks in the universe, so this list is going to be super long. And then you can get into the philosophy of it, like, is the list on the list, you know, these kind of things. The other problem is that there are more than just rocks in the universe, right? The universe has lots of crazy stuff in it. So if you're going to explain what the universe is made out of, you also have to explain why there are leaves and ice cream and blueberries and iPhones, right? And the more you look around and assemble your list, the more you're amazed at the incredible complexity of stuff that's out there, right? We have bicycles and puppies and strangely muscular fellows who become governor of California, right? This guy actually signed my PhD degree, says Arnold Schwarzenegger. So you have to, if you're going to answer this question, you have to explain all of this stuff, right? And that tells you that this approach is not going to work. The approach of just making a list of all the stuff in the universe is not going to work because it doesn't really answer your question. I mean, if you ask me, Daniel, what's the universe made out of? And I actually had a list of everything that was in the universe and I gave it to you, you wouldn't feel like that's an answer. You wouldn't go, oh, cool, I get it, yeah, right? That's not the answer you're looking for. It's like if you ask your teenager, you know, where you're going, and they say, out. Well, okay, technically that's an answer, but it's not a satisfying answer, right? It's not the answer you were looking for, because the kind of answer we're looking for here is a simplification. We're not just wanting to enumerate what's in the universe. We want a simpler description. We want to explain all of this incredible complexity in terms of a smaller set of objects, right? That's the goal. So we don't just make a list, we organize our knowledge. And so here, for example, I've grouped all the living stuff into one category and the rocks in another category. And you can argue with me about if Arnold belongs in the rock category or the living thing category. It's a separate issue. The point is to make an organization and stick with it and look for patterns. So we make a list of knowledge, we organize it, we look for patterns, and then we ask questions about those patterns, and those questions are clues that help us reveal what's going on underneath. Peel back a layer of reality and see the inner workings, right? So fast forward quickly a few hundred years or a few thousand years, if you give the Greeks any credit. Personally, I don't. And you get to an incredible accomplishment, which is you can explain everything you've ever interacted with in the universe in terms of 100 basic building blocks, the periodic table, right? And you might be thinking, okay, this is Harvard Center for Astrophysics. We're supposed to be talking from a particle physicist. Why is he telling us about the periodic table? That's high school chemistry, right? It is basic chemistry. And on the other hand, it's also, in my opinion, one of the most underrated achievements in human intellectual history. Why? Because if your goal is to explain everything in the universe in terms of a small set of objects, going from infinity to 100 is most of the way, right? It's incredible to me that it's even possible to explain this dizzying variety of stuff we see in the universe in terms of just a few basic bits and pieces, right? It's almost like the whole universe is just like a marketing exercise for the Lego company, right? I mean, that's their basic idea, right? Build anything you want out of a few basic pieces, right? It's Legos all the way down here, people. Like you can build dinosaurs, you can build pirates, you can build dinosaur pirates, whatever you like, right? Out of the same building blocks. Why does the universe work that way? Well, we have no idea why, but we're grateful, right? Because it means that it's possible to explain a huge variety of stuff in terms of just a few basic building blocks. And if we're going back to being caveman and cavewoman physicists, we have to have an open mind about what we might have learned, right? It could have been different. It could have been the universe was organized under a different principle, right? Maybe everything had its own little kind of particle, right? Maybe cats were made out of their own little kind of cat particles, and that's why they're so weird. And maybe cartoonists are made out of their own little cartoon particles, right? And llamas and hamsters and everything is made out of their own kind of particle. We could have lived in that universe, but, we don't. And thank God, because it makes my job a lot easier. Okay, so where do we stand? We're looking at the periodic table of the elements. And we don't, again, just list our knowledge and say, here's 100 building blocks, we're done. We organize it and we look for patterns. After all, the periodic table is periodic, right? There are patterns in it. Some of these guys are heavy and some of these guys are light, and some of these guys are very active and some of these guys are very inactive, right? These are the heavy metals over here. And so we look for these patterns because these patterns are going to be the clues that point out what's happening underneath, that explain all the features that we see, right? And of course, all the structures in the periodic table are just emergent phenomena from the structure of the atom, right? The reason the periodic table has the shape it does and the elements have different behaviors over here and over there just come from the structure of the atom. How the electrons fill up those orbitals and how many protons you have, everything comes from the structure of the atom. And I don't tell you this to inform you of this, I'm sure you know it, but to remind you the power of this strategy. That you organize your knowledge, you look for patterns, and then you ask questions about those patterns because those patterns are the clues you need to guide you to reveal the deeper layer of information, right? The fundamental hula hoops of the universe. Exactly. But the atom, of course, is not the most fundamental building block of the universe, and nothing that you see around you, nothing you interact with, is the most fundamental building block of the universe, right? It's not going to be something you're familiar with. At its smallest scale, the universe doesn't work in a way that is convenient and intuitive to you, right? It's not made out of llamas. It's not made out of tornadoes. It's not even made out of llama tornadoes, right? Even though we're going to make a documentary about that for Discovery Channel next year. It'll come on after Shark Week. Yeah. So let's go back to the periodic table, right? It's explained in terms of atoms, and atoms, of course, are electrons whizzing around a nucleus with protons and neutrons. Those protons and neutrons, in turn, are made out of quarks. 2 up quarks and a down, or 2 down quarks and an up, and you have the proton and neutron, which means you can do something amazing. Using just electrons, up quarks and down quarks, you can make any atom, which means you can make anything that you've ever touched or tasted or sat on or eaten, anything with just these 3 particles, right? So how does a particle physicist write a cookbook? Well, you have some up quarks, some down quarks, some electrons, mix, right? That's literally the only recipe you need for anything in the universe. It's an incredible achievement to go from infinite number of stuff to 100 building blocks down to just 3 particles. If your goal is to explain everything, you might think, Well, next week they're going to tell us they found the one particle that rules them all, right? It seems like we're on the verge of figuring it out. You might get that impression. Well, the reason that that's not the case is that there are a lot of wrinkles to this story. And one of the wrinkles is that there are more particles. So we have the up quark, the down quark, and the electron to make normal matter, but there are 4 other quarks, for example. The charm quark, the strange quark, the top quark, the bottom quark. I was not on the committee to name these particles, unfortunately, or I would have come up with better names. The electron is just one example of a kind of particle we call leptons, of which there are also 6. So here we have a new set of particles to wonder about, but we use our same strategy, right? We don't just list our knowledge, we organize it. So we have a new table. This time it's a periodic table of the fundamental particles, right? We organize it and look for patterns, and those will give us clues. So we have the up quark, the down quark, and the electron to start. In this first column, we also include the electron neutrino. Neutrino, a really mysterious little particle. Now, it's not mysterious because it's rare. In fact, neutrinos are everywhere. There's 100 billion, billion with a B, neutrinos passing through my finger every second. In your finger, and your finger, and your finger, right? Everybody's fingers. So why are we not beaten down by all of these neutrinos, right? Why are they not pushing us down? Well, the reason is that neutrinos mostly ignore us, and we ignore them. They pass right through us without interacting. A neutrino can pass through a light year of lead, right? This is the Harvard Center for Astrophysics, so you know how long a light year is. Imagine now a light year of lead, okay? A neutrino can pass through that without hardly noticing. So neutrinos, it's like an alternate universe right here on top of us that we don't even interact with. So we have these 4 particles in the first column. The amazing thing is, of the 12 particles, they align in this way because the charm quark and the top quark are just copies of the up quark. They're exactly like the up quark. They have the same charge, the same spin, all the same quantum mechanical properties, except they're heavier. So the charm quark is like the secret heavy cousin of the up quark, right? And the top quark is like the really, really fat cousin that the charm quark has that's so fat it can't even leave the house, okay? So why does the up quark have these 2 cousins? We don't know, right? They're just there. We just notice this. This just describes what we've observed, okay? The amazing thing is the down quark also has 2 cousins. The strange and the bottom are also just copies of the down quark, but heavier. In the same way, the electron has 2 cousins, right? The muon and the tau. They're just heavier versions of it. There was a point when people understood the up quark, the down quark, and the electron, and people thought, great, we figured things out. And then somebody discovered the muon, and a famous physicist said, who ordered that? We don't need that in our theory. Get rid of it. Sometimes nature is not convenient, right? And the neutrinos also cluster into this same grouping, though their mass relationships is a little bit more complicated. So we have this table of particles, we notice these patterns, and we're going to hope to use these patterns to drill down and figure out what explains them. So these patterns generate questions. Questions like, why do we have all these particles? You need the up quark, the down quark, and the electron to make all the matter, right? Why do we have the other 9? Why 12 particles? Are there only 12 particles? We don't know. There could be 12, there could be 24, there could be 24 million. We don't know if we're looking at the whole ice cube or just the tip of the iceberg, right? There's no theoretical limit to the number of particles that could be out there. To me, one of the really deep questions is why the particles fall into these 3 columns. I'm really interested in when you see a number in physics. So for example, one of the deep goals of physics is to simplify the whole universe into one equation, and you know you're done when that equation is small enough and simple enough that you could fit it onto a t-shirt. Okay, the whole theory of physics on a t-shirt. It's the t-shirt test of physics, okay? So imagine we get there, and you're looking at this equation, and it has a 5 in it. Right? That reveals something about the universe. It means the universe likes the number 5, or there's something 5y about the universe itself, right? So you've got to look at these numbers and wonder about them. So I look at these 3 columns and I wonder, why 3 columns? I ask mathematicians, like, what numbers do you expect in the final theory of physics? And you know mathematicians, they like simple, pure numbers. They go 0, maybe 1, pi, and e. Nobody says they want to see a 3 in that theory. Nobody thinks 3 is a deep number in the universe, unless they're, Catholic or something. And, maybe they're right. Maybe they're right. Who knows? But to me, this seems like a clue, right? It's like there's something going on here. There's some deeper explanation. This is just like in the periodic table. There's a structure here that's pointing us to what's happening underneath. And in 100 years, somebody's going to look back and say, oh, it was so obvious. It was screaming at them right in the face. And yeah, it's screaming at a clue, 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 clue right in the face. We just don't know what it means, right? in 100 years, some graduate student is going to say, oh, I wish I had been a grad student in 2017 when they hadn't figured that out. I could have written 10 papers and gotten 10 Nobel Prizes. It would have been so easy, right? But here we are at the forefront of human ignorance, right? Not knowing what these clues mean and wondering, right? It's much harder when you're actually alive at the time and have to write those papers. Another question is, why are some of these particles heavy and some of them are light, right? We know the Higgs boson is how the particles get mass, but we don't know why it gives some particles a huge serving of mass and others a tiny little bit. There's no explanation for that in the Higgs boson theory. It's an enormous mystery. There's no pattern to these masses. Some of them are thousands of times heavier than the other ones. It makes no sense. One of my favorite ones is this about the electric charges of the particles. So you know the electron is charged -1 just by convention. The quarks have these funny charges, plus 2/3, minus 1/3, but they add up perfectly to make a charge +1 for a proton, right? That's quite convenient, because if the charge is balanced, then you get neutral atoms, you get chemistry, you get biology, you get physics, you get ice cream, and all sorts of good stuff, right? If those charges didn't balance, that wouldn't happen. Now, in the theory of particle physics, the charge of the quarks and the charge of the leptons, totally unrelated. Okay, you are at the control panel of the universe, for example. You can dial those up and down and still get a valid theory of physics. What does that mean? It means that according to our current theory, it's a huge coincidence that these two numbers balance perfectly. We're talking exact balance, right? Not like the sun and the moon in the sky are close enough that you can get an eclipse. That's a 1% coincidence. We're talking exact, perfect coincidence, right? So either it's a cosmic coincidence, or you believe in the multiverse theory or something, or it's a clue that there's something deeper going on, right? That these are actually just two sides of the same coin, or they're built out of the same tiny little Lego pieces that you stumble over at night and step on, right? Something is going on here that we don't understand. But of course, we don't just think about the matter particles themselves, the particles that make up stuff. We also think about how they talk to each other. And before Jorge was particle physicists' favorite cartoonist, we had Richard Feynman, who came up with the Feynman diagram, which really in the end is just a cartoon. It's a way of thinking about how particles talk to each other. Here are some examples. And you can see the solid lines are particles, and the wiggles are how the particles talk to each other. And he came up with this cartoon to think about how particles interact, so we could try to do really precise calculations for how particles bounce off of each other and how they interact with each other with their spin. And these days, we can predict how particles interact, and we can measure how they interact, and those two things agree to 10 decimal places, which is astonishing. If you've ever spent any time in a research lab, you know getting the right answer to within a factor of 2 is like, yay, I can go home and watch Netflix. So to get 10 decimal places right is really extraordinary. It means you really stumbled on something true. It's not just random. It's like, if that was going to happen randomly, it's like the chances of hitting a golf ball in New York and getting a hole-in-one in China. Okay, this stuff just doesn't happen. But we don't measure our theory of physics just by how well does it work, how accurate is it. Remember, we want a theory that fits on a t-shirt, right? We want a really simple, compact theory. So let me show you the current mathematical equation. For the standard model of particle physics, there's another half that wouldn't fit on the screen here. And it feels like, we got a ways to go here, people, right? It's not quite fit. It's be a really extra, extra, extra large t-shirt and extra, extra small font in order to make that work. Okay, but the biggest problem with understanding the answer to the question, what is the universe made out of, is that everything we've learned, everything we've studied, questions included, only applies to a tiny little slice of the universe. It turns out that me and you and ice cream and hamsters and gas and stars and galaxies, all that stuff is less than 5% of all the stuff in the universe. Okay? And so, wow. And we've recently measured with great precision how much of this there is, which means we're in an era of precision ignorance where we've measured very, very well how little we know about the universe. And you might think, that's depressing, right? All this work and we hardly know anything. Well, I think that's exciting because it means there are guaranteed discoveries here, right? There's a whole huge pile of stuff to learn. And to me, that's where the excitement is in this unknown. So let's talk about one of those things. What is this unknown stuff? Well, one of them is dark matter. Dark matter, we first figured out that it was there when we started looking at how galaxies spin. So you can think of galaxies as like massive cosmic merry-go-rounds with ping pong balls on them. What happens when you spin it? Well, the ping pong balls are going to fly out, right? Unless there's something holding them in. So in the case of galaxies, that's gravity. The reason that stars aren't flung off into intergalactic space is because gravity is holding them in. So now you can do something cool, which is you can look at how these galaxies spin, and you can ask, is there enough gravity in them to hold the stars in? So you measure how fast the galaxies are spinning, and then you count up all the stars and you calculate their gravity. You can ask, does it work out? So somebody sent off a graduate student and says, go check this out, make sure it works. I'm sure it works, just go check, please. And they came back and they said, wow, it doesn't work like at all. Okay, there's something really wrong here. It turns out these galaxies are spinning way, way, way too fast. There's not nearly enough stars to give the gravity you need to hold the galaxy together. But obviously the galaxies are not throwing stars into intergalactic space all the time, so what could do it, right? Clearly, there has to be something else in these galaxies, something we don't see, something invisible that has gravity. So they invented this concept of dark matter. Dark meaning we don't see it, matter meaning it has gravity, right? So this is like a favorite trick in physics, is turn a question or a mystery into an idea, right? So what could be invisible and giving us this gravity? Well, how about some new invisible gravity-giving thing, right? That's what dark matter is, right? Dark matter, that's all it means. And these days we don't know very much more about it, other than that it's dark and it has matter. Let's think for a moment about what it means to be dark, to be more precise about it. Well, we know that matter interacts in 4 ways. So gravity, for example, anything that has mass feels gravity, and so they're going to pull themselves together. Things that feel electromagnetism are things that give off light or reflect light. That's most of the stuff in our experience. And then there's the strong and the weak nuclear force. The weak nuclear force is responsible for radioactive decay, and the strong force for holding the nucleus together, right? So what do we know about dark matter? Well, we know dark matter does feel gravity. We invented it to solve this problem of the missing gravity inside galaxies, right? We know it doesn't feel electromagnetism because it's dark, it's invisible, otherwise we would be seeing it, right? It doesn't feel the weak force, and it doesn't feel the strong force. As far as we know, dark matter has no other interactions, right? It could only interact gravitationally. We've tried so many ways to interact with dark matter, and we've never been successful. It doesn't respond to any of my Facebook friend requests. I even tried Twitter. I tried Google Plus people. I was really desperate, okay? There's no way to interact with dark matter. And so 5% of the universe is the stuff we know, me, you, and pies. And in order to explain how gravities are spinning, you don't need to add just a little bit of matter or a tiny little bit of stuff. You need to multiply the amount of matter in these galaxies by a factor of 5, okay? These galaxies are really spinning like crazy, which means that the amount of dark matter in the universe totally dwarfs the amount of what we call normal matter, which turns out to be unusual, weird kind of matter, right? So dark matter is a huge slice of the universe. And it seems kind of convenient explanation, right? You're that graduate student, you get this experimental result. Either you messed up, or you can speculate that maybe the universe is filled with this big invisible thing that makes my experiment go wrong, right? It's sort of a convenient speculation, and it's a big speculation because it's 5 times as much as normal matter. So before people really believed this idea of dark matter, before they convinced themselves, they needed to find other ways to see it, to really prove to themselves it was real. And one way is called gravitational lensing, which is totally awesome. And you use the dark matter as a lens, because dark matter, though it's invisible, it has mass, so it can bend space, so it can act like a lens. So imagine, for example, there's a big blob of dark matter between you and some galaxy far, far away, right? So what happens to a photon that leaves that galaxy and flies up? Well, it gets bent towards your telescope, right, by that dark matter. Another photon that leaves the galaxy in a different direction shoots out and also gets bent towards the telescope. So now if you look in 2 different places in the sky, you see the same galaxy, okay? What does that mean? Well, either you've been smoking banana peels in the philosophy department for too long, or the same galaxy exists 2 places in the universe, unlikely, or there's some big blob of matter that's acting like a lens, right? And that's exactly what we think is happening. And if you go and Google image search gravitational lensing later, you'll see some really stunning photographs. You can see galaxies distorted just like you would expect from a huge cosmic lens. It's really a pretty awesome explanation. But the piece of information that really convinced people, or convinced me, that dark matter was a real thing was a giant collision. So I'm a particle physicist. I like solving problems by smashing stuff together, okay? It's my go-to approach. What's the proton made out of? Smash 2 of them together, let's figure it out. I'm the kind of person who's been taking toasters apart in his kitchen, since he was 7. But when it comes to understanding galaxies, that approach has its limitations, right? You can't go to the National Science Foundation and say, I'd like the money to build a galaxy collider, right? It doesn't really scale. And so astrophysicists tend to have a different approach, which is rather than building the experiment, they just look out into the universe and find it happening already, right? Fortunately, the universe is a really big place. Lots of crazy stuff happening. So that's what happened. They found the bullet cluster, which is this collision of two galactic clusters. Now, galaxy clusters have a bunch of galaxies, each of which has normal matter and dark matter. So what happens when they collide? Well, the normal matter slams into itself, all the gas, huge explosions, just like a Transformers movie, etc. Great special effects. But the dark matter, because it's invisible, it passes right through itself, right? There's no electromagnetic interaction or strong interaction. It just passes right through. It ignores itself. The cool thing is that the normal matter and the dark matter then get separated. We can see this dark matter is there by using gravitational lensing. We use the galaxies that are behind it in the sky. We see them being distorted, so we can see that that's there. This, of course, we see because of the explosions. So now we can see that dark matter on its own has gravity, which means it's not just a mismeasurement of the gravity of normal matter, right? It's its own thing with its own gravity. And that's what really convinced people that we weren't mismeasuring how galaxies rotate, but we really were seeing a new kind of matter that was out there. But what is dark matter, right? We still don't know. We know it's dark. We know it has matter. We know there's a lot of it. We don't know very much more about it. You might think, well, maybe dark matter is a particle. Then maybe dark matter is a particle, but that's a good idea only because everything we've studied so far is a particle. But it's dangerous to extrapolate from everything you know into the unknown, right? Imagine you're a scientist and you're studying the elephant. You spend 300 years studying the elephant's tail, and somebody walks you around to the front of the elephant. They're like, well, maybe you should consider the rest of the elephant, right? If your first explanation is, oh, I think the rest of the elephant is just a bunch of tails, right? Or a perturbation on my tail theory, right? Or a linear combination of tails, you're not going to get the right idea, right? That's the moment when you should throw away everything you thought you knew and start again because you began from an unusual little slice of the data, right? That's the situation we're in, right? So if you say, well, that's a pretty dumb idea, that's exactly what I'm doing when I say maybe dark matter is also made of particles. Well, maybe it's made out of particles, we don't know, but we have no concrete proof that it is. It could be made out of some totally weird new kind of matter that's totally different. Maybe it's not made of particles at all, it's continuous and smooth, we don't know. Or maybe dark matter is made out of particles, but it's a lot of different kind of particles, and those particles have interactions, right? There could be dark physics and dark chemistry and dark biology. There could even be dark life, right? Somewhere there could be a dark physicist saying, we understand 95% of the universe except for this little slice, right? And that's us, They're more common in the universe than we are. We are the unusual bits of the universe, right? So we don't know what dark matter is. We don't know what it's doing. The other thing to remember is dark matter is not out there. It's here with us, right? I have dark matter in my hands right now. I'm not holding it or containing it because it passes right through us. But dark matter follows the distribution of normal matter. Actually, it's the opposite. Normal matter follows the distribution of dark matter because there's more dark matter than normal matter. And the gravitational wells made by dark matter is what seeded the formation of galaxies, right? So we know where dark matter is because it follows normal matter. Okay. But if our goal is to explain what the universe is made out of, so far we've accounted for 5% of stuff we have some idea about. 27% we're pretty clueless, right? We have a couple hints. But that only adds up to a third of the universe. We can't say we explain what the universe is made out of if we haven't even gotten halfway, right? So what about this last chunk of the universe? Well, this is something we call dark energy. But dark energy really is just science code for we have no idea what this stuff is, okay? And the relationship between dark energy and dark matter is literally just the word dark, okay? They have no other connection. So how do we know that dark energy is there if we don't know anything about it? Well, to understand dark energy, you have to know a tiny bit about the history of the universe. So super brief history lesson about the universe, okay? The universe began, all right, there was a big bang, boom, huge explosion, right? Important things happened. And then people were wondering what's going to happen next. Is there enough stuff in the universe, and therefore enough gravity, that things will slow down, stop, and eventually turn around and make a big crunch, right? That could be exciting. Or maybe there's not enough stuff in the universe for that to happen. It's going to slow down gradually and just sort of drift out and get colder and colder and more distant. That's called the heat death of the universe, right? So option A, big crunch. Option B, heat death of the universe. Lots to look forward to, right? So people said, all right, well, let's figure it out. I'd like to know what is the future of the universe. After all, let's go measure it. So what they did is they went out and they looked at supernova and they used that to figure out how fast things were expanding and was that changing over time. And what they figured out is that the universe rejected option A and option B and went for secret option C, okay? Secret option C is neither of these is correct. What's actually happening is that the expansion of the universe is accelerating. every year it's getting faster and faster that things are moving away from each other. Okay, it's not slowing down at all. If you know some physics, you know that for things to accelerate away from each other requires some force, some energy. And we're talking about the acceleration of galaxies here, right? Billions and billions of stars. So no tiny amount of energy is going to accomplish that. That's why it's a 2/3 slice of the universe's energy budget is devoted to shredding the universe and tearing it apart, okay? So we know that it's happening. We know that it takes a huge amount of energy, but we don't have any idea really what's doing it or why it's doing it or the mechanism behind it, right? What could be responsible for pushing these galaxies further and farther apart every year? Right? For some reason, everything in the universe is running away from us faster and faster. No, it's not your jokes, Jorge. Your jokes are awesome. But the fascinating thing is because we don't know what's doing it and we don't have any understanding of the mechanism of it, we can't really predict what it's going to do in the future. We know that about 5 billion years ago, dark energy turned on and started accelerating the expansion of the universe. We don't know if that's going to continue, but we could play some fun games speculating, right? Because dark energy is creating new space between us and other galaxies faster than light can go through that space. Okay, it's like Usain Bolt is running at us at top speed, but somebody's making the track longer, faster than he can run, right? So he'll never get to you. In the same way, these galaxies are getting further and further from us faster than their light can get to us, which means eventually they will become invisible. So as you look up in the night sky, galaxies will begin to disappear. We're talking billions of years in the future. Now, if dark energy is strong enough, it might even be able to pull the Milky Way apart. So imagine 10 billion years from now, astronomers looking up at the night sky, assuming astronomy survives the next 4 years of Donald Trump, right? They're looking up into the night sky and they see nothing, right? A blank, a totally black night sky. How could you possibly do astronomy? How could you look up in the sky and having no idea what's out there, right? We have a huge advantage seeing what we've seen in the sky. Think of all the things we've learned, right? But before you feel too great about what we see in our night sky, remember, we're 14 billion years into the history of the universe, right? What might have appeared in the night sky 10 billion years ago that's now gone forever? Well, we have no idea, and we never will. So we don't know what the future of the universe holds, right? We know that the universe is expanding. We don't understand what's doing it, right? And so we can't really predict what's going to happen next. So here's a summary of our knowledge of the state of the universe. Most of the universe, 2/3 of the energy in the universe is devoted to something, dark energy, we only recently learned we don't know anything about, okay? So huge chunk of the universe we're totally clueless about, except that we know we're clueless about it, right? Dark matter, 27% of the universe, right? We know that it's there, we know it's matter, we don't know very much more about it. And the rest, the etc., this is the part we've been studying for the last hundreds and hundreds of years, right? All that progress we've made is related only to this tiny little slice of the universe. Okay, to me that's amazing. It means that we have so much left to learn, right? It means that future discoveries are going to be totally incredible, right? It seems to me very unlikely that we're going to learn things that are going to be totally boring, right? It's clear that we know very little about the universe. The fraction of the knowledge of the universe we've gained so far is a tiny little bit. It's like you're one of those explorers and somebody tells you, nobody's been to most of the Earth, right? And that's the situation we're in right now. So when I'm telling you that there's a lot of exploration left to be done, I'm not joking, right? There's a lot left to learn. And we're doing everything we can to explore it. We have awesome space telescopes, right, that look deep into the history of the universe and try to understand what happened a long time ago to give us clues about what might be happening now and in the future. We have gravitational wave detectors that see space rippling, which is really cool. We have particle physics detectors that smash particles together. We're going to try to figure all this stuff out before the aliens get here and spoil it for everybody, right? That's the goal. And so I like to think that we're in an era that might redefine our understanding of physics, right? Think about what we might learn in 100 years or in 500 years. If you could steal forwards in time and read a child's astrophysics book, like a kindergarten astronomy book from the year 3000, would contain such shocking truths, right? Basic facts about the universe that we don't know. Imagine the opposite exercise, right? Take a kid's book about astronomy and go show it back in time to Isaac Newton, right? Staggering genius in human history. That guy knew nothing, okay? He knew basically nothing about the human context in terms of how the universe worked and how everything was happening and the history of the universe, the age of the universe, right? Basic things he was ignorant of. We're in that situation now. In 1,000 years, people will look back at us and say, they were primitives, right? They looked up in the sky having no idea about the information that was washing over them, living in such ignorance, right? The way we think about cavemen. They looked up at the night sky and they didn't even realize that they were looking at stars, and all the fascinating information that those stars were beaming at them was just washing over them. They were totally ignorant of. That's the situation we're in today. And I don't say that to you to discourage you, right, or depress you. I say that that's excitement, right? That's a moment of future discovery, right? We know that we know very little, which means we have a lot left to learn. So that's what the book is about really big questions like that. Tonight we talked about one of them, which is just what is the universe made out of? But in the book we tried to tackle a lot of these other questions that are so big that they're rarely often discussed because we know very little about them. You know, things like, what is time? We know time is related to space. We also know it's very different because you can move around in space, but you slide forward in time at 1 second per second no matter what you do, right? Why is that? Speaking of space, you might think, what is space? That's an easy one, right? Space is the emptiness. It's the backdrop. It's the nothing on which the play of the universe happens, right? Except that space can expand. Space can bend. Space can even ripple, right? That's not nothing. Space is a physical, dynamical thing. It has all sorts of properties we haven't discovered. It's like, imagine you were a fish scientist. You've been swimming in the water for 1,000 years and thinking, water, that's nothing. That's just the emptiness, right? We need to learn anything about the water, right? Then you discover, ooh, it has interesting properties. It's actually pretty important, right? That's the situation we're in with space. Only recently have we figured out that space is a thing. We have questions like, why can't we travel faster than light? And why isn't the speed of light 1,000 times what it is, or a 1/10 of what it is, right? According to our knowledge, you could dial that up or down and still have a theory of physics that worked. So the point of the book is not to tell you about all the things we do know, but to excite you about all the things we don't know, because it's in what we don't know that lie mind-blowing future discoveries. So thank you very much.
We have time for a few questions. We'll start here.
So in your example of the galaxies colliding and the dark matter separating out, and you mentioned the galaxies that are colliding rip themselves apart and cause turmoil. Mm-hmm. But that turmoil is caused by gravitational interactions between the stars and the gases in the galaxy.
Most of that turmoil is caused by electromagnetic interactions. Because the electromagnetic interactions that hold those particles together and make them the gases into a plasma and all that kind of stuff. If you just have gravitational interactions like dark matter, then you just pass right through each other because gravity is so weak.
So it's the gases that are interacting because there aren't really that many star collisions that go on. So it's the interaction of the
Most
gases.
of the gas that does.
Okay. I guess.
Yes.
Is it possible that dark matter could be something like black holes? Could black holes have the same effect of gravitational lensing that and all that kind of stuff that you described that all kind of would go into it? Because when I think of like when they did the calculations of the spinning of the galaxies, they didn't really know of black holes that much at that time, so they really probably didn't put it into their calculations. So could that take over dark matter and not actually be what it is?
So could dark matter be made out of black holes? Short answer is yes, it could. Favorite theory is this thing called primordial black holes, meaning black holes created during the Big Bang that are left over. A lot of physicists think that that's ruled out because of blah, blah measurement, and other physicists think those physicists are totally wrong. Right, so there's a big argument about whether primordial black holes are still a valid theory of dark matter. But so the short answer is, yeah, they could be, absolutely. We know very little about dark matter. Great question.
We have another question over here.
If the galaxies are receding so fast that the light doesn't get there, doesn't that mean they're going faster than the speed of light?
Great question. So there's a very hard and fast rule. Nothing can travel through space faster than the speed of light. But there's a caveat, which is you can always create more space. And you can create space at any speed. So you can create space. There's no limit to how fast you can create space. So you can't move through that space faster than the speed of light, but you can create new space fast enough that light will never get there. It's like you're building more track for Usain Bolt who never gets to the finish line.
Next time I get a speeding ticket, can I use that?
Yes. I'll give you my cell phone.
What is the approximate distance two galaxies would have to be apart for them to eventually not see each other? Like how far apart do they have to be?
How far apart do galaxies have to be so they never see each other? It's a great question. Instead of thinking about the distance, because
Or how much space needs to be in between?
right, instead of thinking about the distance, you should think about the relative velocity. Because it's more about the relative velocity than the distance. No matter how far apart two galaxies are, you will see one from the other one if you have enough time. But if they're moving fast enough away from each other, or more accurately, the space between them is being created faster than the speed of light, so that's the answer, then the light will never make it. So that's the answer, is if the space between them is being created faster than the speed of light, then they'll never see each other again, they'll disappear. Now some of these galaxies used to be within our observable universe. That's back before dark energy turned on. Then dark energy kicked on, it's pushing them out past the edge of our observable universe.
How much space has to be in between two galaxies right now for them to be right on the edge of almost seeing each other?
Yeah, so the size of our observable universe is tens and tens of billions of light years. So pretty far.
I imagine that you have to simplify a lot of really complex ideas for this book. Are there any topics that you didn't touch on because you didn't feel like you could simplify it enough? Or any topics which you feel like you're going to get a little bit of pushback because some of your colleagues might say, oh, well, you should have introduced these 15 caveats?
That's a great question. The guiding principle for the book was that we wanted to only talk about things where you could understand the question with no explanation. Like we wanted to have the chapter titles be, what is space? Well, everyone wants to answer. How big is the universe? So they have to be really basic in terms of the question. In terms of the answers, we know a lot about this stuff, and we ran it by some colleagues, and we collected all of their caveats in advance. So there are a lot of questions. For example, there's questions about the mysteries of neutrinos. Neutrinos are really fascinating, but we felt like it took 5 pages to explain why neutrinos are fascinating, and so they didn't really feel like these were pretty tough. Great question.
One more question.
You discussed quarks and leptons, but not bosons.
Right, so we talked about the matter particles, the particles that make up stuff. There are other particles that those matter particles use to talk to each other. Those are the bosons. So for example, the photon is a boson for electromagnetism. Each of those 4 kinds of ways particles interact have bosons associated with them that shoot stuff back and forth. So they're not the matter particles, they're more the force particles.
Right. But have we discovered all the bosons that exist?
We've discovered the bosons for electromagnetism, for the weak force, and for the strong force. We have not found one for gravity. People have a name for it already. It's called the graviton, but nobody's seen it. We don't even know if gravity operates in that way by passing bosons back and forth. It's a big mystery. And of course, if dark matter has some new interaction, it might also have a new boson, which somebody would get to name.
Okay, I think that's it for questions now, but they'll be hanging around. You can come ask your questions.
Buy a book, we'll answer any questions.
That's like we'll answer more questions.